that makes a reaction spontaneous. We've seen in the second law of thermodynamics that a reaction which is spontaneous will increase the entropy of the universe. And so a reaction that does increase the entropy of the universe is going to be spontaneous. And so when talking about the entropy of the universe, we need to consider that it is equal to the entropy of the system plus the entropy of the surroundings, because the universe is the system and its surroundings. And so consider 4 different scenarios where in the first case, our system, our reactants and products, the chemicals that are reacting themselves, they increase in entropy during the reaction. And additionally, as the reaction occurs, it releases heat. It's exothermic. Now, if it releases heat, it will also increase the entropy of the surroundings as well, because it's heating up the surroundings. They'll increase in temperature. The particles in those surroundings will move faster. They'll have greater entropy. So in this case, where both the entropy of the system and the entropy of the surroundings increase, the entropy of the universe will increase as well. In this case, that reaction will necessarily be spontaneous at all conditions. But consider our bottom case here, in which the entropy of our system, so the particles reacting themselves, decreases. They start moving around less and less, per se. But additionally, that reaction, it absorbs heat as well. It cools down the surroundings. It makes the surroundings have a lower temperature, and hence the particles of the surroundings will move less and less. They'll also have a decrease in entropy. In this case, where both the system and the surroundings have a decrease in entropy, the entropy of the universe will decrease as well. And so, under no circumstances will this reaction be spontaneous. You'll never get much more product than reactant, although the reaction can go to some slight extent, perhaps. But consider these 2 middle cases. Before we do that, though, consider that the entropy of the surroundings matters more at low temperature. This is because consider you're at a low temperature, say 0 Kelvin. If you're at 0 Kelvin and you add a little bit of heat to that, you might increase the temperature to 10 Kelvin, but that might result in a pretty dramatic change in entropy, because originally your particles were not moving at all, and now they're moving somewhat. If you're at a low temperature, adding a little bit of heat can make larger effects on the entropy of particles. And so consider the first case, in which the entropy of your particles, your system, increases, but the reaction absorbs heat. That is, it cools down the surroundings and makes the surroundings have a decrease in entropy. Now in this case, the increase in the entropy of the system supported spontaneity because it increased the entropy of the universe, but the decrease in the entropy of the surroundings does not support spontaneity. In fact, it opposes spontaneity because it decreases the entropy of the universe. We have 2 counteracting forces here. And so the entropy of the universe, it's a combination of these 2 forces, and these 2 forces are partly dependent upon what temperature you have. Now, remember that at low temperatures, the entropy of the surroundings matters more. So at low temperatures, this might have a greater value than that. So at low temperatures, the entropy of the universe will decrease. But at high temperatures, this entropy of the surroundings has less effect, and so the entropy of the system has greater effect. At high temperatures, that entropy of the system overwhelms the entropy change of the surroundings, and so the entropy change of the universe will be positive. You'll have an increase in entropy of the universe. And so that reaction will increase the entropy of the universe and hence be spontaneous only at high temperatures. An example of this is one in which we take solid water and we melt it into liquid. Now in this case, taking solid to liquid, that increases the entropy of your particles. Now they're moving around a lot more, those particles that were reacting themselves. But this reaction is also endothermic. It absorbs heat from the surroundings and cools them down, decreasing their entropy. Now this melting of water is spontaneous, but only at certain temperatures. It's only spontaneous at high temperatures, above 0 degrees Celsius, if you're at if you have 1 atmosphere of pressure. So this is an example of such a system. But going through another example, and in this case, it's liquid water is freezing, and that releases heat. The entropy of your particles themselves decreases, turning from liquid to solid. They move less. But being that that is an exothermic process, that increases the entropy of the surroundings. And so we have two counteracting forces here again, one negative, one positive. Which one wins? We'll recall that at a low temperature, this entropy of the surroundings matters more, and so at low temperature, the entropy of the universe will increase. But at high temperatures, the entropy of the surroundings will decrease. We can see that this freezing process will occur at low temperatures, below 0 degrees Celsius. Now, these are all nice ways to view things, and I think a key component is that an increase in the entropy of the system and releasing of heat by that reaction, those both support spontaneity. And so we can consider that later in the Gibbs free energy equation. But first, let's derive that. So we know that for a spontaneous process, the entropy of the universe must increase. It must have a change which is greater than 0. And we know that this entropy of the universe is equal to the entropy of the system plus the surroundings. Excuse me, this is surroundings. Now, the entropy of the surroundings, it's actually equal to negative delta H of the system over the temperature. This is saying that when more heat is released by the reaction, that will increase the entropy of the surroundings more. Because when you're releasing more heat to the surroundings, you're increasing its temperature more, and so you're increasing its entropy more. But this is also saying that dividing by temperature, having a lower temperature, you'll have a greater effect on the entropy of the surroundings by a certain amount of heat being released by the system. The lower the temperature, the more effect that heat will have, and it will increase the temperature. Will increase the temperature of the surroundings and have greater effect on the entropy of those surroundings. So that's just really saying, hey, at a low temperature, you can dramatically increase the entropy of your surroundings by the addition of just a little bit of heat, i.e., the heat released by the reaction increases the entropy of the surroundings more at low temperatures. So we can take this original equation and now replace entropy of the surroundings with the negative enthalpy of the system over the temperature. And then we can multiply both sides by, I think it's negative temperature, and get the following reaction. Where now we get, actually by positive temperature, and we can rearrange to get this equation, which can be reinterpreted to give this, and now we can say that we can replace this negative temperature times the change in entropy of the universe as being delta G. This is the change in Gibbs free energy. This is really the important equation, and you don't have to be able to derive it, but the change in Gibbs free energy tells us about the spontaneity of a process. Delta G is equal to delta H of the system minus temperature in Kelvin times the entropy change of the system, so of the particles reacting. Now, this is just saying that the spontaneity of the process depends upon how much heat is released or absorbed by it, the temperature, and the change in entropy of your particles themselves. And so G is that Gibbs free energy. Now, we know that in order for a reaction to be spontaneous, we had seen that all of this had to be greater than 0, but multiplying by -1, all of this has to be less than 0. In order for the reaction to be spontaneous, delta G has to be less than 0, and that is a key point. Delta G, if it's negative, if it's less than 0, that means that we have a spontaneous reaction, and so the reaction will proceed significantly if it gets started. And so when it reaches equilibrium, we're going to have mostly products. The reaction is spontaneous. It proceeds significantly. We'll have a lot of products versus reaction when equilibrium is reached. If delta G is equal to 0, the reaction is at equilibrium. And if delta G is greater than 0, then that is a non-spontaneous process. The reaction is not going to proceed significantly by the time equilibrium is reached, and so you're going to have mostly reactant, not product, when that equilibrium is reached. And so consider 4 cases again. One in which we have the entropy of the system increasing, and it's releasing heat, just as we've seen in that table up top. In this case, both of these things support spontaneity. We have an exothermic reaction that supports spontaneity, like the combustion of wood, say, and the particles are increasing in entropy. Now, in this case, we should get a negative delta G. Why is this? Well, plug in negative delta H, and then subtract temperature times a positive delta S. You have a negative minus a positive, or that's a negative and a negative combined. Delta G is going to be equal to negative value. And so that is going to be leading to a spontaneous reaction. If both of these things support spontaneity, then you will have a spontaneous process. Whereas in the bottom case, where we have a positive heat, so it absorbs heat, it cools the surroundings down, and our particles themselves decrease in entropy, that reaction is not going to be spontaneous because neither of these things support spontaneity. Consider where you have a positive delta H, and you're subtracting temperature times a negative delta S. Positive, and then negative times negative is positive. We have a positive plus a positive, that gives us a positive delta G. That is going to be positive always, that's never spontaneous. But these other cases, we have negative and negative, and it really depends upon the temperature. If temperature is 0, such as at low temperatures, you can cross this out. So cross out all that at low temperatures. What do you have? Delta G is equal to delta H. If you have a negative delta S, delta H of the reaction, then your delta G is negative as well. And so it's spontaneous at low temperatures, but not spontaneous at high temperatures. And then if your temperature were infinite, then it would be opposite, and delta H would have no value. At a high temperature, delta G would be negative, and that would be not spontaneous. And then you can surmise the rest about this. Thanks for watching, guys.